Hello guys, in this tutorial I am going to explain the electric field distribution in a cylindrical insulation which has multiple layers of insulation. This problem is continuation of my previous video where I explained the electric field distribution in a typical cable insulation which is cylindrical geometry. Therefore, before watching this video, please refer to my previous video. The video link is given in the description. Before I can start, I want to remind you that in cylindrical insulation, our electric field is inversely proportional to the radial distance from the surface of the conductor. So, if we plot the electric field as a function of r, radial distance, then electric field behaves like this. So we have maximum electric field at the surface of the conductor, and then it is inversely proportional to the radial distance. And inside the conductor, which is this region, inside the conductor, from the center to the surface of the conductor, electric field is 0. And if we have multiple layers of insulation, like this given case, then electric field behaves like this. And at every boundary, wherever the insulation changes, where we have another layer of different insulation material, then electric field jumps to its maximum value and then it decreases. Okay, so this is how the electric field behaves in multiple layered insulation, cylindrical insulation. Okay, now this maximum electric field Emax depends on the permittivity of the material. Okay, not only one insulation but permittivity of all the insulations. This is what we're going to study in this video. So let's read the problem statement. In the problem statement, we are given a conductor which is shown here. So this is the conductor with a diameter of 30 millimeter, and then we have one layer of insulation which is a hardboard shell, and its permittivity is relative permittivity is 4.5. Then so this is epsilon r1, which is 4.5. This is epsilon r1. Okay, then this shell is enclosed in an oil container with 100 millimeter diameter, this outer cylinder, and its relative permittivity is 2.2. So this is epsilon r2 and relative permittivity is 2.2. Now, how many percent does the field strength E on the surface of the metal conductor decrease due to hardboard shell? So, without the hardboard shell, we will have electric field distribution like this. If we have only oil surrounding the whole conductor, and then if we have hardboard shell and another layer of oil, so then our electric field will behave like this. So these two electric fields, Emax1 and Emax2, will lie at a different level. So electric field, maximum electric field at the surface of the conductor will be different in both of these cases. So in this question, we need to determine how much percent the electric field strength on the surface of the metal conductor decrease due to the hardboard shell. Okay, so before we start, let me write the formulas which we derived in the previous lecture, in the previous video. So electric field can be written as total charge Q over 2 pi epsilon L R. Okay, and potential difference between 2 points can be written as E dot dr and r from point 1 to point 2, or from the inner radius to the outer radius. Okay, so these are the expressions which we will use to solve this problem. Okay, let's start first without the hardboard shell. So without hardboard shell, we will have only conductor, and it will be surrounded by oil with relative permittivity epsilon r2. And so in this case, our inner radius will be 30 millimeter, uh, 30 divided by 2, so 15 millimeter, and outer radius will be 50 millimeter. Okay, so now in this case, our electric field will be E will be equal to Q over 2 pi, because now we have only one insulation, which is oil, so we will use permittivity of oil only, which is epsilon 2. Here we will use absolute permittivity, so it will be absolute permittivity epsilon 2 instead of epsilon r2, and L length of the cylinder, and multiplied with r. So that will give us electric field at any arbitrary distance r from the center of the conductor, where r is greater than r1, which is 15 millimeter. Okay, now the now we have here unknown q. Okay, so let's suppose this is q1. We have q unknown, and also we know that Emax, maximum electric field, occurs at the surface of the conductor. So q1 over 2 pi epsilon 2 L r1, that is the surface of the conductor. Okay, now we need to determine the value of q. For that, we will solve the expression for electric field. This is our equation 1. So we will solve this equation. We will use this equation to solve for the voltage. So we know the voltage applied. So applied voltage is equal to, from R1 to R3, which is the outermost radius. We have just one layer of insulation. So that will be Q1 over 2 pi epsilon 2 L R1. Sorry, here we will take R as a variable. dr. Okay, so if we solve it and substitute the values, we will get, substitute the limits, we will get q over 2 pi epsilon 2 L natural log of r3 over r1. Okay, now we will rearrange this equation to get the value of q1. So q1 will be equal to 2 pi epsilon 2 pi epsilon 2 L U over natural log of R3 over R1. And then we will substitute the value of Q1 in our electric field or maximum electric field expression, equation 1. So putting this in equation 1, we will get E max 1 equal to U over R1 natural log of R3 over R1. So this is our E max 1. Okay. So we found E max 1 here. Now we are going to evaluate the second case where we have hardwood shell to determine E max 2. Okay. Then we will calculate the percentage difference. So with the hardwood shell now, with hardwood shell, we have the center conductor, we have hardwood shell, and then we have oil. So here we have R1, then here we have R2, then we have R3. So this is my conductor, this is my epsilon 1, this is my epsilon 2. So this will be my geometry now. Now again, the electric field at the center of the conductor, maximum electric field, E max 2 at the center of the conductor will be equal to, similar to the previous expression. Now here we will have Q2 because now our insulation has changed, so charge distribution will also change. So now I am representing it by Q2. So Q2 over 2 pi epsilon 1. Now the insulation surrounding the conductor has permittivity epsilon 1. In the previous case where we did not have any cardboard shell, so we had whole oil surrounding the conductor. There we had permittivity of oil, so we used epsilon 2. Here we have to use epsilon 1. Okay, and L, and again the radius of the conductor is R1. Now here we need to, this is my equation 2, so we need to find Q2 in order to uh, solve for the percentage difference between Emax1 and Emax2. Now the total voltage applied, so we have the total voltage here, okay, which is being divided. So if this is U total voltage, now this will be divided between the two layers of insulations, so it will have U1 and U2. Okay, so now my total voltage will be equal to U1 plus U2. Again, using the relationship, this relationship, we can find U1 and U2. So U1 will be equal to Q over, so Q2 over 2 pi epsilon 2 L R dr, and limits from R1 to R2. We are Here, this expression gives us U1, that is the voltage in the voltage across the insulation layer 1, which is hardboard shell. And here we have to use Q2 divided by 2 pi epsilon 1 instead of epsilon 2. This is epsilon 1 L R dr plus, now we need to find the voltage across the insulation layer 2. For that, we need to put again Q2, because total charge for both layer is the same, divided by 2 pi. Now here we will use epsilon 2 because we are in the insulation layer 2, epsilon 2 Lr dr, and now the limits will be from R2 to R3. So, because we are in the outer layer, so R2 to R3, and then by solving it and putting the limits, we will get U is equal to Q2 over 2 pi L 1 over epsilon 1 natural log of R2 over R1 plus 1 over epsilon 2 natural log of R3 over R2. Okay, then we can rearrange this equation to get the value of Q2. So Q2 will be equal to 2 pi L U over 1 over epsilon 1 natural log of R2 over R1 plus 1 over epsilon 2 natural log of R3 over R2. Okay, so then putting this value of Q2 in our equation 2, we will get E max 2 equal to U over R1 natural log of R2 over R1 plus R1 epsilon 1 over epsilon 2 natural log of R3 over R2. So this is our E max 2. Okay, now we will find the percentage difference. So percentage difference of maximum electric field, that will be E max 1 minus E max 2 divided by E max 1 multiplied by 100. So that will give you approximately 31%. So 31% reduction in electric field will be resulted if we add a layer of hardwood shell. Now, while you put these values for Emax 1, Emax 2, remember we have everything given in the question, but U is not given, but U will be anyway cancelled because U will be here at the numerator and at the denominator. U will be in Emax 1, Emax 2, and at the denominator Emax 1. So U will be cancelled, everything is known. So we are given the permittivities, we are given relative permittivities, but here in this formula you have to use the ratio of absolute permittivity, and the ratio of absolute permittivities is equal to the ratio of relative permittivities. Now in part B, we need to find the voltage in each of the layer U1 and U2. Okay, so for the voltage we need to use the same expression with the hardwood shell. this one U is equal to, we found this expression already. So U equals to Q2 over 2 pi L 1 over epsilon 1 natural log of R2 over R1 plus 1 over epsilon 2 natural log of R3 over R2. Okay. So, and what about the voltage in layer 1? So voltage in layer 1, U1 is equal to, as we used here, this was the voltage in layer 1. Okay. So if we solve it, we will get Q2 over 2 pi L epsilon 1 natural log of R2 over R1. So you can get the value of Q2 from here, by rearranging the equation and then putting in this equation. Okay, then plugging the values, you will get U1 equal to approximately 20 kilovolt. Now total applied voltage is 50 kilovolt. So if total applied voltage is 50 kilovolt, U1 is 20 kilovolt, then U2 will be 50 minus 20 equal to 30 kilovolt. So in layer 1, 20 kilovolt will be dropped. In across layer 2, there will be a potential difference of 30 kilovolt. That's all. Thank you.